Hello friends, welcome to our RV YouTube channel. Myself R Venkatesh. In today's session 34 of Electric Drives and Control, we are going to discuss about operation of 6-step voltage source inverter under 120 degrees conduction mode. This 6-step voltage source inverter is also known as 3-phase bridge voltage source inverter. This inverter can be operated in two modes of operation. One is 180 degrees conduction mode of operation and another one is 120 degrees conduction mode of operation. In this session, we are going to discuss about 120 degrees conduction mode of operation of a voltage source inverter. In our previous session 33, we have discussed about V by F control of a 3-phase induction motor, where we discussed in order to perform a V by F control, we are in need of a voltage source inverter. Therefore, in this session, we are going to discuss about operation of a voltage source inverter. So first, let us discuss about the circuit diagram of a 3-phase voltage source inverter. So this is our circuit diagram. This Vs is the fixed DC input voltage. Basically, an inverter converts a DC input voltage to an AC supply voltage. So this fixed DC input voltage, which is of a value of Vs, will be converted into AC supply and which will be fed to the stator windings of this 3-phase induction motor. So here this A, B, C represents the 3 phases of the stator windings of this 3-phase induction motor. And this capacitor C, which is used to filter the harmonics. Here thyristor T1, T2, T3, T4, T5 and T6 along with these diodes forms the 3-phase bridge voltage source inverter. Now let us discuss about the operation of 3-phase voltage source inverter, under which first let us discuss about the switching pattern of the thyristors. So as we discussed earlier, an inverter has to convert a DC input voltage to an AC output voltage. So here this Vs is a DC input voltage with the value of Vs, and this Vs, which is nothing but a DC input voltage, will be converted to AC output voltage called VAV by using an inverter. So this is a stepped wave AC output voltage. So this AC output voltage is classified from 0 degrees to 360 degrees with the equal interval of 60 degrees. So to produce this AC output voltage from 0 degrees to 60 degrees, we have to make thyristors T1 and T6 to conduct. And to produce the AC output voltage from 60 degrees to 120 degrees, we have to make thyristors T1 and T2 conduct. And in order to produce the AC output voltage from 120 degrees to 180 degrees, we have to make the thyristors T3 and T2 to conduct. And in order to produce the AC output voltage from 180 degrees to 240 degrees, we have to make the thyristors T3 and T4 to conduct. And in order to produce the AC output voltage from 240 degrees to 300 degrees, we have to make thyristors T5 and T4 to conduct. And similarly, in order to produce the AC output voltage from 300 degrees to 360 degrees, we have to make thyristors T5 and T6 to be conducted. So if you look at this switching pattern table, each thyristor will be conducting for 120 degrees. For example, if you look at this thyristor T1, this thyristor T1 is conducting from 0 to 60 degrees and also from 60 degrees to 120 degrees. Therefore, this thyristor T1 is conducting from 0 degrees to 120 degrees. That is, this thyristor T1 is conducting for 120 degrees. So in the same way, all the other 5 thyristors is also conducting for a period of 120 degrees. Hence, this mode of operation is known as 120 degrees conduction mode of operation. Operation of 3-phase voltage source inverter is classified into 6 modes of operation. So first let us discuss about first mode of operation. As we discussed earlier, in order to produce the AC output voltage from 0 degrees to 60 degrees, we have to make thyristors T1 and T6 to be conducted. That means we have to give the gate pulse for the thyristor T1 and T6. So what happens is, this thyristor T1 will be connected to the positive terminal of the supply voltage, and if you look at here the circuit diagram, this is connected to the A phase of the load. Therefore what happens is, when thyristor T1 conducts, this thyristor T1 is connected to the positive terminal of the supply voltage, and this thyristor T1 will be connected to the A phase of the load. And this T6, thyristor T6 will be connected to the negative terminal of the supply voltage and B phase of the load. So that is drawn here as an equivalent circuit. So this thyristor T1 is connected to the positive terminal of the supply voltage and the A phase of the load here. And similarly, this thyristor T6 is connected to the negative terminal of the supply voltage and B phase of the load. So here VAN can be written as Vs by 2. See here the supply voltage, that means the DC input voltage is Vs. And here we have assumed the load to be as an impedance load. That means the three-phase induction motor. Since the value of the impedances of all three phases are same, this supply voltage will be equally split. So when the thyristor T1 and T6 are conducting, the A phase and B phase will be connected to the supply side. Therefore, since the values of this impedances of A and B phases are same, this supply voltage Vs will be equally divided for this A phase and B phase. Therefore, we can write the phase voltage VAN as Vs by 2 and VNB as Vs by 2. That means half of the value of Vs. And here the voltage between the line A and B is nothing but VAB. So that VAB can be written as Vs. See here, the supply voltage Vs and the output voltage is VAB. That means the line voltage is VAB. So this Vs will be appearing across this line voltage VAB. That means across the load. Therefore, we can write VAB is equal to Vs. So based on this, now let us write the phase voltages here. So from the circuit, we have found that VAN is equal to Vs by 2. So that is written here. VAN is equal to Vs by 2. And from the circuit, we have found that VNB is equal to Vs by 2. So that is written here. VNB is equal to Vs by 2. So we can write the phase voltage VBN as minus VNB. Therefore, what happens is VBN is equal to minus, instead of VNB, we can write Vs by 2. Therefore, what happens is the B phase voltage VBN is minus Vs by 2. And when the thyristors T1 and T6 conducts, the C phase of the load will not be connected to the supply. Therefore, see here, see in the equivalent circuit, the C phase is not connected. Only A phase and B phase is connected when the thyristor T1 and T6 are conducting. Therefore, we can write VCN as 0. Now, let us calculate the line voltages based on the values of this phase voltages VAN, VBN and VCN. So, from the circuit, it is found that the value of VAB as Vs. So, that is written here. The line voltage VAB is Vs. The line voltage VBC can be written as VBN minus VCN. Therefore, VBC is equal to the value of VBN is minus Vs by 2 and the value of VCN is 0. So, after substituting the value of VBN and VCN, we will get the value of VBC as minus Vs by 2. The line voltage VCA can be written as VCN minus VAN. So, therefore, VCA is equal to the value of VCN is 0 and the value of VAN is Vs by 2. So, after substituting the values of VCN and VAN, we will get the value of VCA as minus Vs by 2. Now, let us discuss about the second mode of operation. That is, in order to produce the AC output voltage from 60 degrees to 120 degrees, we have to make thyristors T1 and T2 conduct. That means we have to provide gate pulse for the thyristors T1 and T2. So when the thyristor T1 conducts, this thyristor T1 is connected to the positive terminal of the supply voltage and it is connected to the A phase of the load. And when the thyristor T2 conducts, this thyristor T2 is connected to the negative terminal of the supply voltage and C phase of the load. Okay, so that is drawn here in the equivalent circuit. So this thyristor T1 is connected to the positive terminal of the supply voltage and A phase of the load. And this thyristor T2 is connected to the negative terminal of the supply voltage and C phase of the load. So as we discussed earlier, since the values of all the impedances are same, here A phase and C phase will equally divide this supply voltage Vs. Therefore, the phase voltage VAN becomes Vs by 2 and the phase voltage VNC becomes Vs by 2. And the line voltage VAC, that means the voltage between A and C is nothing but equal to Vs. So that is written here. VAC is equal to Vs. So now let us write the phase voltages. So from the circuit we have found that the phase voltage VAN is equal to Vs by 2. So that is written here. VAN is equal to Vs by 2. And from the circuit we have found that the value of VNC is equal to Vs by 2. So that is written here. VNC is equal to Vs by 2. So the phase voltage VCN can be written as minus VNC. Therefore, what happens is VCN is equal to minus and the value of VNC is Vs by 2. So if we substitute this VNC is equal to Vs by 2, then becomes the value of the phase voltage VCN as minus Vs by 2. And coming to this VBN, when this thyristors T1 and T2 conducts, the B phase of the load will not be connected to the supply. Therefore, we can write VBN is equal to 0. See here in the equivalent circuit, you can find that there is no B phase connected to the supply voltage. Therefore, we can write VBN is equal to 0. Now, let us try to calculate the line voltages based on this phase voltage. So, here VAB, the line voltage VAB can be written as VAN minus VBN. So VAB is equal to the value of VAN is Vs by 2 and the value of VBN is 0. So after substituting these two values, we will get the line voltage VAB is equal to Vs by 2. And the line voltage VBC can be written as VBN minus VCN. So the value of VBN is 0 and the value of VCN is minus Vs by 2. So after substituting these two values, we will get the value of VBC as Vs by 2. And VCA can be written as minus VAC. So from the circuit we have found that VAC is equal to Vs. Therefore what happens is the value of the line voltage VCA is minus Vs. Now let us discuss about the third mode of operation, that is from 120 degrees to 180 degrees. So in order to produce the AC output voltage from 120 degrees to 180 degrees, the gate pulse for the thyristors T2 and T3 are given. So when the thyristors T2 and T3 conducts, the B phase and C phase will be connected to the supply voltage. Therefore, we can write the phase voltages as VAN is equal to 0, VBN is equal to Vs by 2 from the circuit diagram, and VCN, that means VNC is equal to Vs by 2 from the circuit diagram, from which we can obtain our VCN as minus Vs by 2. So the line voltages based on these phase voltages can be written as VAB is equal to minus Vs by 2, VBC is equal to Vs from the circuit diagram, and VCA as minus Vs by 2. And now let us discuss about the fourth mode of operation, that is to produce the AC output voltage from 180 degrees to 240 degrees. The gate pulse is given for thyristors T3 and T4. So when the thyristors T3 and T4 are conducting, the B phase and A phase will be connected to the supply voltage. Therefore, we can write the phase voltage VBN as Vs by 2 and VNA as Vs by 2, and the line voltage between the phase B and A, that is VBA as Vs. So based on this, now let us write the phase voltages. So the phase voltages here, VNA is equal to Vs by 2 from the circuit, which is written here. So VAN becomes minus Vs by 2, and from the circuit it is found that VBN is equal to Vs by 2. And VCN, that is the C phase will not be connected to the supply when the thyristors T3 and T4 conducts. Therefore VCN can be written as 0. So now let us calculate the line voltages based on this phase voltages. That is nothing but VBA, that is VBA is found to be Vs from the circuit diagram. VAB is equal to minus VBA, therefore VAB becomes minus Vs. And VBC is VBN minus VCN. So after substituting the value of VBN and VCN from here, that is VBN is equal to Vs by 2 and VCN is equal to 0. So after substituting these two values, our VBC becomes Vs by 2. And the line voltage VCA can be written as VCN minus VAN. So the value of VCN is 0 and VAN is minus Vs by 2. So after substituting these two values, our line voltage VCA becomes Vs by 2. Now let us discuss about fifth mode of operation. To produce the AC output voltage from 240 degrees to 300 degrees, thyristors T4 and T5 are made to conduct. So when the thyristors T4 and T5 conducts, the C phase and A phase of the load will be connected to the supply voltage. Therefore, we can write the phase voltage VCN as Vs by 2 and VNA as Vs by 2. And the line voltage between C and A, that is the line voltage VCA, can be written as Vs, which is written here. VCA is equal to Vs. So now let us write the phase voltages. So from the circuit it is found that VNA is equal to Vs by 2. So which is written here, VNA is equal to Vs by 2. The phase voltage VAN can be written as minus VNA. Therefore, the value of the phase voltage becomes, A phase voltage VAN becomes minus Vs by 2. When the thyristors T5 and T4 conducts, B phase will not be connected to the supply. See here in the equivalent circuit there is no B phase, only A and C phases. Therefore, VBN can be written as 0. And from the circuit it is found that VCN is equal to Vs by 2. Therefore, the phase voltage VCN is Vs by 2. And now let us calculate the line voltages based on this value of the phase voltages. So VAB can be written as VAN minus VBN. So the value of VAN is found to be minus Vs by 2 and the value of VBN is found to be 0. So after substituting the value of VAN and VBN, our value of VAB becomes minus Vs by 2. So the line voltage VBC can be written as VBN minus VCN. So the value of VBN is 0 and VCN is found to be Vs by 2. So after substituting the value of VBN and VCN, the line voltage VBC becomes minus Vs by 2. From the circuit it is found that VCA is equal to Vs. So that is written here, the line voltage VCA is equal to Vs. Now let us discuss about the sixth mode of operation. That is to produce the AC output voltage from 300 degrees to 360 degrees, the thyristors T5 and T6 are made to conduct. So when the thyristors T5 and T6 conducts, the C phase of the load and the B phase of the load will be connected to the supply voltage. So we can write the value of the phase voltage VCN as Vs by 2 and the value of VNB as Vs by 2, and the line voltage between the line C and B, that is VCB, as Vs. So that is written here, VCB is Vs. So now let us write the phase voltages. So when the resistors T5 and T6 conducts, A phase will not be connected to the supply voltage, so that you can see in the circuit. So there is no A phase, only C and B phases are present. Therefore we can write VAN is equal to 0. And from the circuit it is found that VNB is equal to Vs by 2. So that is written here, VNB is equal to Vs by 2. So VBN can be written as minus VNB. Therefore our VBN becomes minus Vs by 2. And from the circuit we have found that the value of the C phase voltage as Vs by 2. So that is written here, VCN is equal to Vs by 2. So now let us calculate the line voltages based on these values of phase voltages. VAB can be written as VAN minus VBN. The value of VAN is found to be 0 and the value of VBN is found to be minus Vs by 2. So after substituting the value of VAN and VBN, we will get the value of the line voltage VAB as Vs by 2. And VBC, the line voltage VBC can be written as minus VCB. From the circuit we have found the value of VCB as Vs. Therefore what happens is we can write VBC as minus Vs. And finally the value of the line voltage VCA can be written as VCN minus VAN. The value of VCN is found to be Vs by 2 and VAN is found to be 0. So after substituting the value of VCN and VAN, we will get the line voltage VCA as Vs by 2. Now let us draw the output phase voltages based on the discussion of individual modes of operation. So I have made a tabular column of the values of the phase voltages VAN, VBN and VCN with period wise based on the previous modes of operation discussion. So here this is our DC input voltage, that is Vs, which we have given as input to the inverter, and this VAN and VBN and VCN are the AC output voltages which we obtained from the inverter and which it is fed to the three phases of the stator windings of the induction motor. So if you look at this tabular column, the value of VAN, that is the value of the phase voltage VAN from 0 degrees to 60 degrees is Vs by 2. So that is drawn here, Vs by 2. The value of VAN from 0 degrees to 60 degrees is drawn as Vs by 2 in the red color. So this Vs by 2 is the half of the value of this Vs. And from 60 degrees to 120 degrees, the value of VAN is found to be Vs by 2. So that is drawn here, Vs by 2. Okay, with the value of Vs by 2 from 60 degrees to 120 degrees. So from 120 degrees to 180 degrees, the value of VAN is 0. So it is 0 here. And from 180 degrees to 240 degrees, the value of VAN is minus Vs by 2. So that is drawn here, minus Vs by 2 in the negative axis. And from 240 degrees to 300 degrees, the value of VAN is minus Vs by 2. So from 240 degrees to 300 degrees, it is drawn as minus Vs by 2 in the negative axis. And at last, the value of the phase voltage VAN from 300 to 360 degree, it is found to be 0. So that is drawn here. So in the same way, the phase voltages VBN and VCN can be drawn based on this values of the phase voltages VBN and VCN in the tabular column. Now let us draw the line voltages of output voltages. So as we discussed earlier, this is our fixed DC input voltage which is given as input to the inverter, and these are the line voltages which are obtained from the inverter. So this is, I have made a tabular column of the line voltages VAB, VBC and VCE based on our previous discussion in the individual 6 modes of operation. So first let us draw the line voltage VAB. So from 0 degrees to 60 degrees, the line voltage VAB is found to be Vs. So it is drawn here, Vs. So this Vs is equal to the value of this input Vs. And from 60 degrees to 120 degrees, the value of VAB is Vs by 2. So here it is drawn from 60 degrees to 120 degrees, it is drawn as Vs by 2. That is half of this value. And from 120 degrees to 180 degrees, the value of VAB is minus Vs by 2. So that is drawn here, minus Vs by 2 in the negative axis from 120 degrees to 180 degrees. And from 180 degrees to 240 degrees, the value of VAB is minus Vs. So that is drawn here, minus Vs in the negative axis from 180 degrees to 240 degrees. And from 240 degrees to 300 degrees, the value of the line voltage VAB is minus Vs by 2. So that is drawn here, minus Vs by 2. And from 300 degrees to 360 degrees, the value of the line voltage VAB is Vs by 2. So that is drawn here in the positive axis from 300 degrees to 360 degrees. The value of the line voltage VAB is Vs by 2. So in the same way, the line voltages VBC and VCA can be drawn based on this tabular column. So this is how a three-phase voltage source inverter operates. Thank you.